And we are back. And now, in our last video, we talked about the magnitude of the force felt by a charge that is moving in a magnetic field and is moving, of course, in some direction relative to that magnetic field. This time, we're going to talk not about the magnitude of that force, but instead about its direction. So let's imagine a charged particle. We'll make it a positively charged particle that is moving with a velocity, and I'll pick a direction for it to be moving. Let's say that away in this magnetic field. As that charged particle moves in that direction, it feels a force. This equation describes the magnitude of that force. You'll notice that V times sine theta is actually just the component of this velocity that happens to be perpendicular to B. So as far as the magnitude is concerned, all that really matters is the perpendicular component of the velocity, not the entirety of the velocity, which is a good thing to remember. Now let's think about the direction of the force that this feels. One of the interesting things about the magnetic field force, also known as the Lorentz force, you might see it called some other places, is that the direction of the velocity, or the component of the velocity that matters, the direction of the field, and the force are all mutually perpendicular. So all that matters is V perpendicular, that's the component perpendicular to the B field, but the force is also perpendicular to both of those things. Now, take a moment and ask yourself, how can the force be perpendicular to both V and B? We're back from our pause, I hope. And what we can assume then is if the force, the velocity, and the magnetic field are all perpendicular to each other, the only way for that to be true is for the force to be either into the board or out of the board. Those are the only two options. Well, as it turns out, the force has a direction that can be determined using a nice simple rule. And that nice simple rule is called the first right-hand rule. I'm going to put my right hand into the picture now, and we're going to use my right hand. Now, when you read the text, by the way, you'll see a different way of talking about this, and I apologize for that. I just think this is an easier way to describe in video and in person. I'm going to put my right hand into the picture, and my fingers are pointed in the direction of the magnetic field. North to south, that's the same direction as from my knuckles to the swirls on the ends of my fingertips. So, pointing your finger in the direction north to south in your magnetic field, pointing your fingers in the direction of those field lines is step one to using the right-hand rule. Your thumb will indicate the direction of the velocity that is perpendicular to that field. So I'm going to put my thumb perpendicular to my fingers, like so, and we see that the velocity is then towards the bottom of the board. The force, that's where the third vector in this discussion comes in. The force is the direction my palm is pushing. So with the field right to left and the velocity towards the bottom of the page, my palm is pushing down into the board. Well, until now, we haven't had to worry about a direction of a vector that's not on the plane of what we're talking about. So we need to come up with a way of discussing a vector that is into or out of the board. And of course, we have a way of talking about that. To do that, a force that is into the board, by convention, we're going to represent with an X inside a circle. As I just drew that pink X, and F, of course, indicating that that direction represents the force. that is kind of like an arrow going into the board. And I like to think of it as looking at the back of an arrow that you just shot into the target, and these X's kind of represent the feathers, if you like to think of it that way. And that is our first right-hand rule. Let's take a little pause. And when we come back, we're going to look at some different scenarios. And we are back. And now we see a positively charged particle moving left to right in your picture, while the magnetic field, north, is at the bottom of our picture, south is at the top, magnetic field lines by convention, pointing north to south, and we want to figure out what's the direction of the force acting on that charged particle. Well, we can once again apply our right-hand rule. I'm going to point my fingers in the direction of the field, my thumb in the direction of the velocity, and now we see my palm is pushing up towards the ceiling. That is the direction of the force. And just like before, we're faced with the problem of finding a way to depict a force that is not on the plane, but instead is coming out of the page. We used an X for something going into the page. For coming out of the page, it's simply a dot. Now I like to put the dot inside a circle. This way, the dot kind of looks more intentional. If I just left a dot there, you might think I just left a dot by accident. So the dot inside the circle is the force, or whatever vector it is, coming out of the board. We'll do some exercises on this in a non-video format, but this is the direction of the force a moving charge feels while it is in a magnetic field. Thanks for watching.